So this is going to be a lesson about the trigonometric identities. Trigonometric identities, just like any identities, relate the outputs of functions at different places. Now, because the trigonometric functions are defined on a circle, it's going to make sense to exploit some of the symmetries of a circle. To have any meaningful discussion about the unit circle, we should start by actually drawing one on. The first identities I'm going to talk about are the periodic identities. Now, the periodic identities are actually the simplest identities. They basically tell us that if we go all the way around the circle and come back to our starting point, none of the trig values will change. Since going around the circle one full time doesn't cause the x-coordinate to change, then we can say that the cosine of theta is equal to the cosine of theta plus 1 rev. Now, since making a full turn doesn't cause the y-coordinate to change either, then we can say that the sine of theta is also equal to the sine of theta plus 1 rev. Now, since the gradient is just y divided by x, then we know that the tan of theta also equals the tan of theta plus 1 rev. You can go around as many times as you like, and as long as you end at the same place, you'll still have the same cosine, sine, and tangent. Now, remembering that 1 rev is the same thing as 2 pi radians, we can rewrite all of these in radians as well. Finally, we can use the fact that there are 360 degrees in 2 pi radians to rewrite all of these in terms of degrees as well. Now, whilst this is reasonably straightforward, let's go ahead and test it with a calculator just to make sure that it makes sense. We'll start by setting our calculator to degrees, and then we'll just type in something random like sine 20. Now, just to mix it up a little, I'm going to go ahead and subtract 360. So 20 minus 360 is minus 340. So as we can see, the sine of 20 degrees is just the same thing as sine of minus 340 degrees. Now, the next lot of identities also exploit a symmetry of the circle. So let's go ahead and make a new page to show you how that one works. Of course, we're going to need the unit circle, so let me just grab it from the previous page. The next set of identities we're going to talk about are going to be called the supplementary identities. Now, to begin with, supplementary angles are two angles that add to 180 degrees or half a revolution. So now I'll go ahead and draw on some angle theta and its supplements on the unit circle. Now I can show you that these are supplementary by moving the rightmost angle to the left. As you can see, when you add these two angles together, you get a whole semicircle, as we wanted. So I'll go ahead and put these two back, and then I'll label them. Now if we try adding up these two angles, we'll see that they do in fact add up to pi. In the first line I just took this angle, and then added it to this angle. Then I removed the brackets, and then I showed that it's just equal to pi. So we can go ahead and get rid of this as well. Now I'll go ahead and draw the coordinates of these two rays and their gradients. Now if we look carefully at these 2 points, we notice that they have different x-coordinates. However, if we look at the y-coordinates, we notice that they're exactly the same. As for the gradients, they're negatives of each other as well. We can mark all of this information on the diagram too. Now, since x is the same thing as cos, and y is the same thing as sine, we can go ahead and label these coordinates in terms of cos and sine. Now, since the cos values are just negatives of each other, we can write down the following identity. Now, since the y-coordinates are exactly the same, we can write a similar identity for sine, except there's no negative sign. Now finally, since the gradients are negatives of each other, we can also say that the tans are negatives of each other as well. Now you might wonder what would happen if the points were here or here. In truth, there's nothing wrong with putting the points here, so let me go ahead and give you an example of the points being in all 4 of these places. So to clarify, we want to write all three of these using only pi on 9 radians. So let's start by labeling these A, B, and C and drawing on a sketchy unit circle to show where they all are. We'll also have to show the points at pi on 9 radians. If we turn our attention to the first angle for a moment, we can see that this missing angle is the same as the angle over here. Since we're just comparing the x-coordinates, we notice that this side is positive and this side is negative, so that means these two are just negatives of each other. Now we can go ahead and test this out with our calculator. First, I'll type in the left-hand side. Now we can go ahead and type in the right-hand side as well with the minus sign. As you can see, both the left-hand side and the right-hand side give minus 0.9397. I'm going to go ahead and get rid of the calculator, and I'm going to trust you to go ahead and check all of the other values. For part B, I better go ahead and convert it into radians. We know that there are pi radians in 180 degrees, so we can use that to make the conversion. If we actually go ahead with the conversion, we'll notice that this is just the same thing as 8 pi on 9 radians. This again means that this angle is the exact same as this angle over here. Now because of the symmetry of the circle, we can see that these two will just have exactly the same y-coordinate, so their signs must be identical. Now we can get rid of this and try part C as well. To begin with, we know that a rev is just the same thing as 2 pi rad, so we can go ahead and make that substitution first. If we cross this 18 with the 2, it'll become 9 at the bottom, so we can write this as 17 pi on 9. That means that this leftover angle is also pi on 9, just like this angle. So when we compare the gradient of this line to the gradient of this line, we again notice that they're just negatives of each other. Now there's nothing special about pi on 9 radians. I could have chosen any angle, and you can repeat these steps for pretty much any of the trig ratios you like. Now the identities that we've learned in this lesson aren't the only identities that we can apply to trig functions. There are actually many more. So this completes our discussion of your first trigonometric identities.